In this video, I will give you an example of Ampere's law. Or in other words, I will we will find out the magnetic field due to a long current carrying wire, and we'll do this one by using the Ampere's law. So what we are given is a very long, infinitely long of current carrying wire. Okay, and we are interested in finding out the magnetic field at this point here. So what we given is just a wire here, just a wire, and then we have to find out the magnetic field at this point P, and this is a long wire, and the distance between them is R. So this is a wire, that's the point where we need to find out the magnetic field and the distance here. So what we do here, by using the Gauss law, we draw an imaginary loop. So this is my imaginary loop, and you can draw in fact any closed loop, but the simplest one, if you choose the simplest one, then the life becomes so easier to integrate. Okay, so I have chosen a circle here, a circle or loop enclosing the current I here, and this is in the form of a circle. Okay, and if you look, by using a right hand rule, then the magnetic field at any point due to this current carrying wire is given in this direction here. All right, so you have to use a right hand rule here. And how do you find out the current direction? If you hold the wire and your thumb has to point out in the direction of the current, then the direction in which your fingers curl gives you the direction of the magnetic field. So in this case, the magnetic field at this point is in this direction, the magnetic field at this point is in this direction, and the magnetic field at this point is in this direction. And now look at the elementary length, the length here. The elementary length here is in this direction here. Sorry, I think the system hung up, so just be patient with me. Okay, so the elementary length at this point is in this direction. The elementary length at this point is in this direction here. So at each point, the magnetic field and the DL length are in the same direction. Both are in the same direction. All right. So now, how do I write down the Ampere's law? This is the Ampere's law here. This is this line integral. That's the magnetic field, dl vector equals to mu naught I enclosed. And if you have just a current carrying wire, and if it is a circle, that means each point is exactly at the same distance. That means the magnetic field, just by symmetry, will be exactly the same. The magnitude of the magnetic field will be the same at each point, and that's the reason we chosen this circle. If you do not choose a circle, if you take any arbitrary shape, you can still apply the Ampere's law. But now, as the distance vary at each point, the magnetic field will be not constant, and it will be quite difficult to integrate. So what I'm trying to say here, B vector and dl vector. If it is a circle, then this magnetic field is constant at each point. So I'm taking out. And this is a dl vector, B vector dot dl vector, and B vector and dl vector are in the same direction. So A vector dot B vector is equal to AB cosine theta. Right? If it is in the same direction, then cosine is 0, so it will be simply equal to AB. So that is what it is here. Okay, and that's the reason we choose this circle here. And also look at the angle at each point. At each point, B vector and D vector are in the same direction. If you choose any other complicated closed loop, then the B vector and the dl vector might not be in the same direction. There could be an angle between them. So it won't be, you won't be able to find it out that way, or it will be extremely hard. So choosing your imaginary Ampere's loop is extremely important. Okay, so in this case the simplest is choose the a circle here. So now dl vector, what is this dl vector means? That is the total length here. This is, remember, this is a line integral. So now if I just enclose dl vector, that will be the total length of the circle or circumference, which is equal to 2 pi r. And this I enclosed here, so the loop, this loop here encloses only one current, or only one current is passing through this loop here, which is I. So I enclosed is I. So now if we solve for B, it will be equal to mu naught I divided by 2 pi r. And see how it is, how simple it is to find out the magnetic field due to a current carrying wire. We did exactly the same thing by using the Biot-Savart law. It was quite complicated, and this is quite simple to use. And the direction, again, if you have to find out the direction of the magnetic field, it is always using the right hand rule. In this case, it is encircling the wire. Okay, so if you hold your wire so that your thumb points out in the direction of the magnetic field, then your fingers curl in the direction of the magnetic field. So this is now the magnetic field due to a long wire. Now you might be wondering why you always talk about the long wire. I mean, this would exactly hold for the short wire too. So why you did not talk about the short wire? Here is the answer. Now see, if I choose a short wire, okay, not in long wire, then what happens? There is the fringe magnetic field. Here I'm talking about fringe magnetic field. Fringe magnetic field. And due to the fringe magnetic field, the magnetic field at each point and the dl vector may be in the different direction. So you have to take this one into account here. Okay, so just, and if you choose a long wire, so the magnetic field due to the fringe's magnetic field will be negligible, will not be taken into this consideration. But if you take the short length of the wire, then you have to consider the fringe magnetic field too. The more the short the wire is, the fringe magnetic field will be highly significant. But if as the length of the magnetic field, as the length of the wire is bigger and bigger, the fringe magnetic field will be significantly smaller or negligible. That's the reason we choose a long wire. So this is it from this video. If you have any questions, write down your question in the comment section below. Do not forget to like, share, and subscribe the channel. Thank you.